Welcome to the video on Graphical Behavior 2, Day 1. In this video we're going to focus on concavity. So Graphical Behavior 1 focused on increasing, decreasing, and the extrema of a function. And in here we're going to focus on concavity. So as a reminder, concave up is a function that kind of creates a cup, and concave down is a function that kind of creates a frown. So let's get to it. Our primary objective today is to figure out how to find our concave up and concave down intervals. So at the end of this lesson we should be able to do that given a function. Example 1. Let a function be defined such that f prime of x is greater than 0. So what does that mean? If f prime is greater than 0, we have a function that is increasing. And they want us to draw 3 different ways in which the graph might appear. So let's try this out. We have just a line. There we go. That function is increasing. We also have a parabola. Let's see, like e to the x, not a parabola, but an exponential. That's a function that is increasing. And another one that we might have is log of x. So there we have 3 functions. And what we have when we look at this, here, the rate that we are increasing is constant. This one, we are, let's see, we're increasing, but we are increasing the amount we're increasing by, or maybe a better way to write that is the slope is increasing. So down here we have like a slope of almost 0. Then we have a slope of 1, and then we have a slope of 2, so the slope is increasing. And then finally, in this last one, our slope is decreasing. So we started out with a slope of, maybe a slope of 2 there, and then a slope of 1, and finally we're decreasing to a slope of almost 1, or almost 0 actually. So each one of these indicate a different type of concavity. This one, there is no concavity because it's not creating a frown or a cup. This one, we have concave up. The tangent lines are beneath the curve, or you could say that the slope is increasing. And we'll come back to that definition as the slope is increasing because that's a good way to think of this. And then we have concave down here. The slope is decreasing, or the tangent lines are above this function. So this idea of a decreasing slope, what that is saying is that f prime is decreasing. And if we want to know when a function is decreasing, we take the derivative, and the derivative of that is negative. So what is the derivative of f prime? Well, the derivative of f prime is f prime prime, and if we want that to be negative, f prime prime is less than 0. So when the second derivative is negative, then the slope is decreasing and the function is concave down. And that's what is going on in this table here. If a function is continuous, then what we can get is the concave up behavior is when the second derivative is positive, and the concave down behavior is when the second derivative is negative. And what I've put together here is what I call the fun chart. It showed up in the last section a couple times, and it's a handy way to organize the relationship that you have with functions and their derivatives. When a function is concave up, the derivative is increasing and the second derivative is positive. When a function is concave down, the derivative is decreasing or the second derivative is negative. And then the second column here says when a function is increasing, the derivative is positive. When a function is decreasing, the derivative is negative. So this is a great way for us to organize our thoughts, especially when we get to taking a look at the graph of the derivative and making predictions about the function. We've done this a little bit where we saw like, hey, the derivative is positive, so what's that mean for the function? It means that the function is increasing. So we will use this throughout this section, and hopefully you can use this chart to help organize your thoughts. All right, let's roll to the next page. All right, so there's basically, if a curve exists, there's 4 kinds of behaviors it can exhibit that include concavity. And this first one, the curve is increasing, and we know with increasing curves we get a first derivative greater than 0. We also have an increasing curve right here, so this first derivative is greater than 0. And then what we have is concave down. Because this function is concave down right here, our second derivative is negative. And this function here is concave up, so our second derivative is positive, or greater than 0. Switching to the other 2 pieces, we have a function that's decreasing, so our first derivative is going to be negative, and this function is also decreasing, so our first derivative is negative. And this function is concave down, so our second derivative is negative, and this one is concave up, so our second derivative is positive. So some people like to use this chart to help remember them. I hope that by the end of the lesson we'll have been using them enough for you just to naturally have this memorized. But the idea is first derivative tells us increasing, decreasing, and second derivative tells us concave up, concave down. All right. When a function changes from concave up to concave down at some point, that point is called an inflection value. So the x-coordinate is the inflection value. The x-coordinate is the inflection value, and then the whole pair is the inflection point, which sometimes I will call the POI, the point of inflection. So if the second derivative changes from positive to negative, we have a point of inflection if the function exists there. So looking at this diagram here, what we have is we have concave down behavior switching to concave up. So we have an inflection value at x equals p, and we have a point of inflection at the x-coordinate and then the y-coordinate. This one here, we got concave up to concave down, so that's also an inflection point there. This one we have concave up to concave up, so that is not an inflection, no inflection. And then this one, and the last one, we have concave down to concave up, so you'd want to say that it's an inflection value, but the function does not exist there, so we can't talk about an inflection point there, even though concavity changes. So in this lesson, what we're going to do is we're going to work at learning how to find these possible inflection values and then test to see if it actually is an inflection value. So let's get to it. So possible inflection values are going to occur where the second derivative is 0 or the second derivative does not exist. So we need to find, just like we did critical values for the derivative, possible inflection values. It's the same process, except now we're setting the second derivative equal to 0. When we're labeling concavity, concavity can change either at one of these PIVs, possible inflection values, or at a discontinuity. So we saw that in the last drawing. We had concavity change at a discontinuity. Not every possible inflection value indicates a point of inflection. So sometimes we find these possible inflection values and they just don't change the concavity. Kind of like critical values didn't also necessarily change the increasing, decreasing behavior. All right, this box here describes how we test for concavity, and if you want to come back and visit this after we've done an example, this kind of walks us through exactly what we're going to be doing. Basically, we're finding the critical values of the derivative, so it's very similar to our increasing decreasing, but we're doing it for the second derivative. Okay, let's do it on example number 3a. All right, for the sake of saving space and time, we're going to strike these two problems. It's probably worth trying to work them out yourself, but in the sake of the video, for the sake of the video, I'm only going to focus on a few of these. All right, the first derivative here is y prime is equal to derivative of sine is cosine x. And then we want to find the second derivative because we're looking for possible inflection values. So the second derivative is negative sine of x. And we want to set the second derivative equal to 0 to find possible inflection values. And we see that when we solve that equation, we have possible inflection values at x equals 0, pi, and 2 pi. Now what we want to do is test those possible inflection values in the same way that we tested our critical values for increasing decreasing. So 0, pi, and 2 pi, and we are going to test it on the second derivative. So if we plug a number between 0 and pi into the second derivative, we get a negative answer, so it's concave down right there. And if we stick a number between pi and 2 pi, it's a positive answer, which is concave up. So we tested like negative sine of 4, and we got a positive answer. So here we have it, the possible inflection values of 0, pi, and 2 pi. We got a change of concavity at pi. So what we have is a point of inflection. There we go. A point of inflection at pi, comma, what is f of pi? We stick pi in here, we get 3 plus sine of pi is 3 plus 0, so 3. There's our point of inflection there. We can't consider whether 2 pi is a point of inflection because we don't know what the function is beyond 2 pi. But if this was not constrained, I suspect it's just going to alternate between concave up, concave down, etc. So there we have our point of inflection, and we can also conclude that we are concave up from, let's do open intervals, concave up from pi to 2 pi, and concave down from 0 to pi. And because we're good at our parent function transformations, we can think of what this graph looks like. It is a sine function that's been shifted up 3 units. So there's 2, 3, and 4. And we see that from 0 to pi we have concave down behavior, and from pi to 2 pi we have concave up behavior. So understanding our parent function transformations really help us support that our findings are correct. And we have this point of inflection right there. Okay, let's see if we can tackle the same process on number D, or part D. And I'm going to zoom in here. And I think I want to do D and E. So we'll get to work on that. Starting with the first derivative, we get f prime is equal to 4x to the third minus 12x squared, and then the second derivative is equal to 12x squared minus 24x. And I'm going to pause it here and give you a chance to try to tackle this one on your own. So starting there, take over, go ahead and pause it now. Alright, so we took the derivative, second derivative, set it equal to 0, found our possible inflection values, ran through and found the sign of the second derivative in each of the given intervals. Then we identified our points of inflection and our concave up and concave down intervals. So this is a fourth degree polynomial, and I suspect if we were to draw this, we probably would have something that does that. That's roughly how fourth degrees, and we see that we have two portions of concave up and one portion of concave down. So that kind of aligns with our understanding of polynomials. Okay, part E. We're not going to do part F. It's just a little bit too easy. So let's do part E. I'm going to give you a chance to try to tackle this derivative and second derivative on your own. So go ahead and pause the video here. Alright, so we took the derivative, used the product rule, derivative of the first times the second, first times the derivative of the second, to get our second derivative. We factored out the e to the negative x squared and found our possible inflection values. And now we test those possible inflection values, and we're going to put negative root 1/2 and positive root 1/2. And against our second derivative, what we get is positive, negative, positive. So we see that what we have is points of inflection at negative root 1/2, comma, e to the negative 1/2, and also one at root 1/2, comma, e to the negative 1/2. Our concave up and concave down intervals are split at those points, so we're concave up from negative infinity to negative root 1/2, as well as root 1/2 to infinity, and we are concave down between those values, negative root 1/2 to positive root 1/2. And I don't really know what this graph looks like off of parent function transformations, so I turned to my calculator to see what it looks like, and it looks kind of like the bell curve. And there actually, I believe, is a relationship between this equation and the bell curve. But what we get is concave down behavior right in the middle, and then concave up behavior on the outer edges. So that works out. Alright, finally example G. And I'm going to let you try to tackle G completely on your own, and then we'll compare it against what I put in the video. So go ahead and pause the video now. Alright, we took the derivative, and then we used the second derivative, and we have a discontinuity for the second derivative at x equals 0, so that's a possible inflection value. And finally, we test it, and we find that we are concave up, and then concave down. So concave up, concave down, and we draw our conclusion. We have a point of inflection at 0, 0. We're concave up from negative infinity to 0, and we are concave down from 0 to infinity. And that aligns with our understanding of parent functions. The cube root function looks like that. We see a point of inflection right there at the origin, and we are concave up on the left side, and we are concave down on the right side. So there we go. Okay, I'm not going to show the calculus on this one, but I'll leave it to you to tackle on your own. thinking about what this function looks like, this piece is the square root function that has been reflected, so we get something that looks kind of like that, and then this is a parabola, so we get something that looks kind of like that. And so based off of our parent function understanding, we should be concave down from negative infinity to 0 and concave up from 0 to infinity. So I'll leave the calculus to you to try to tackle on that one, and hopefully you arrive at this answer. Alright, thanks for watching the video. From this you should know that we use the second derivative to determine concave up behavior and concave down behavior, and that the point where it transitions from concave up to concave down is called a point of inflection. And until next time, have a good evening.